So yeah, so there are many contributors, of course, to this area. Here I'm listing the point of contact. Here I'm listing just a point of contact I mentioned again through the slides. So yeah, this is just a depiction of the kind of capability that we have. So we have some utilities like for Saccado failings, for automatic differentiation, and for DAG for managing the field evaluators, and then we have a core on mainly finite element discretization, although we support a little bit of finite volume, and this is mainly the package like in Intrepid for local assembly, and Penser for more like global and assembly and other things. We have we rely on mesh tools, which are stick for the mesh database, and also we have Krino supports a lot of things like level sets, but also mesh refinement and mesh adaptivity. In terms of discretization, we also have a Compadre, which is a package for mesh-free discretization, and it's used also for data transfer, especially so if you have a field that you want to transfer from a mesh to a cloud of points or vice versa, that's pretty useful. You have scheme tempos for time integration, and then finally we have some tools for analysis, like kind of outer loop kind of work, and in particular for sensitivities optimization, the rapid optimization library, and for uncertainty quantification, Kokkos. The packages with a star are packages that are standalone. They have their own repo, and they are snapshot into Trilinos. So those are Roll, Stick, Krino, and Compadre. So in terms of the kind of where we are in the updates, we have been working last year a lot on finalizing this IPETRA archival. In particular, we wanted to make sure that we have enough coverage of testing coverage when archiving IPETRA. So we a lot of packages in this area work on like converting tests to like TPETRA. And then the other thing is we also got rid of of Intrepid, which is the initial package for local finite elements, and in particular roll tests were all based. Well, the one using partial differential equation were all based on Intrepid, so there was quite a bit of work to transition to use Intrepid too. Other broader efforts have been like the refactor of views and what basically Roger mentioned before, for automatic differentiation type to support the new MD span, and in anyway all like trickle down effect from the Kokkos change to MD span. There've been some active porting on SQL, and in particular Roger is also working on that. And yeah, so something that I don't know if it's been mentioned before, I don't know if Kurt mentioned, but so we have a Trilinos update paper. Of course, this project-wide effort, and I think it's been finally accepted for publication. So in terms of updates in different packages, so in Intrepid 2, we have been doing some performance improvement and refactory to address the Kokkos changes in Kokkos. Christian Trott did a lot of work and also in Trilinos, and in particular in Intrepid too, but there were still some lingering issues. In particular, Roger mentioned this kind of fairly technical thing of using malloc view to get some properties of the views that is not reliable anymore. So we had to change a lot of code for to be compatible with that. And then we've been some work on doing performance optimization to leveraging the structures, and I'm gonna talk a little bit about this. And there is this paper that has been accepted. It should appear. I don't know when, but I don't know. Do you know when it's gonna appear? No. Okay. But yeah, at some point it will appear. And there's some ongoing work on having fast high order matrix free operations, and yeah, I'll touch on it later. Okay, so and now the other thing is we are going to support shell elements. This is for based on a requirement from STIC. So shell elements is essentially some very thin elements. I think of 2D elements, but in 3D space that are very thin, and they can be treated as 2D elements, but you are still in a larger manifold, so there are some technicalities there. Okay, so just want to give, what's the time?
You're about 7 minutes in.
Yeah, but it's 5 minutes away from the break. Okay, so so yeah, just want to give a little bit of a deep dive in Intrepid 2, the work that mainly Nate Roberts has been doing in the last few years on having some structure-aware optimization in Intrepid. So when you write a finite element code for a structure mesh, is a lot. You have to be pretty general, and so a lot of times you discard some structure for generality purposes. For example, if we typically evaluate the Jacobian from the reference to physical map on each quadrant points because it can be different. But if you have an affine mesh, then you know that the Jacobian is constant on each element. And so so this work by Nate is really to try to exploit this structure and be more effective both in terms of memory usage and performance, CPU performance. And so these are kind of and the way to do that is to define new data structure and algorithms, and while keeping pretty much the same interface. And so this is like classic. So for example, for a cubature, in Intrepid, the quadrature rules are called cubature. Well, I don't want to go there, but so the classic implementation. It's like in Intrepid 2 we use dynamic Kokkos or dynamic rank views. So you want to define the dynamic rank view for the point, for the weights, and then you can invoke this get cubature for a given cubature rule, and you fill up these points and weights. The new structure-aware implementation, you have some data structure. In this case, there are these tensor points and tensor data, and you get that you can automatically allocate these points and weights. You don't really know what they are. Depends on the curvature. They might be. So, for example, if you are in hexahedra, the quadrature points will be a tensor product of 1D. The quadrature rules will be a tensor point of 1D quadrature rules, and so you might just store a 1D quadrature rules instead of the full 3D, which would be like n to the 3 kind of size. And so this is much more better in terms of both memory usage, and then you can use it in algorithms to squeeze out some performance. These are like one of the typical approach in finite element is to use some factorization. And this helps you with performance again by exploiting the structure. This is a table that from an MFM paper where you can see the theoretical advantage of going from a classic like finite element assembly plus MATVEC to use some factorization and then like a partial assembly with the matrix-free action. And you can see you could get pretty significant gains. So for example, for the assembly, you go from P is the order of the finite element, and D is the dimension. So you go to P to the 3D, to P to the 2D for some factorization, to P to the D for partial assembling and matrix free. So we want to get this to try to achieve these speed ups, these performance improvements. So and yeah, so for example, if you think of a hexahedra or even wedge elements, you can write the basis, both the basis function and the quadrature rules as tensor products of lower dimensional basis function and quadrature rules, and you can get a lot out of it. So this is some results, and they're still from Nate Roberts, and so we are comparing like the basic computation of the natural norm square of the H-curve elements, which will be like the dot product of the integral of the square and the curl operator, and then and you can see in as a function of the order of the finite element, and you can see on OpenMP and CUDA the speed up compared. So in blue you see the standard implementation, and in red the sum factorized one, and on the y-axis you have the time. You can see huge speed up. So in the case of CUDA, you are close to like 2 order of magnitude speed ups when you go up with high order finite elements. And now we are working on partial assembling with matrix-free math-back operators, and we're also working with Christian Glusa to use a matrix-free pre-multigrid preconditioner to use this to solve like Laplacian kind of problems or more complicated problems. Okay, so yeah, it should be already in the break. But so I go through this pretty quickly. So Roger already mentioned the work done in Saccado, so I'm gonna skip it. And also Roger is also working on the SQL support. In failing, beyond the work related to Kokkos, we want to support share space. So there was an option in Kokkos to have a UVM by default, and this has been removed. So in order to support that, now we have to support share space. Unfortunately, these are not a backward compatible change. So there have been some issues with that, but it's being worked on. And then in terms of Panzer, there have been some workflows. So I mentioned, for example, we recover the transit optimization support and some caching option for the connectivity for a connection manager, and I think the plan work is to continue improving this transit optimization capability, and then performance improvement for ATS4. In Piro, which is sort of a wrapper for enabling both forward and like analysis kind of problem, and we've been again working. It's basically what I mentioned before. So the Petra, getting rid of Petra and improving some capabilities. And now as well, here is where we're going to work on transit optimization. And Stokkos, it's now only in maintenance mode. So besides the refactoring of the ensemble type because of the Kokkos moving to MD-span, we've been some of the PC like polynomial skulls expansion classes have been removed, and also all the stochastic hierarchy support will be probably removed. We're not gonna. There is no plans to implement that in Petra. In terms of compadre, we now support heap. And then in terms of ongoing work, there is an implementation of RKPM. So now it's currently based on moving least squares, and so we want to go to also provide RKPM implementation. And for ROL, the rapid optimization library, as I mentioned already, the issues with the Petra Intrepid, and now one thing maybe worth noticing is that they're finalizing a first comprehensive paper about ROL, and which should be out on archive soon. Yeah, and then these are other snapshot packages that are snapshot into Trilinos. I don't want to mention much about these. I will leave these as references. So I know, like with Stick, we're also collaborating with them for this Stick transfer, where they want to do mesh transfer outside of Sierra, and so we're helping them. They're using a little bit more of an Intrepid too for that, and then Krino is done a pretty well developed package. And in particular, they added some tools for mesh refinement and adaptive refinement, and there's other things they're working on. So I think that's it. Yes, and I'm listing again the contributors and sponsors. Hope I was quick enough.
You got started late. We're into the break, but any questions?
For high order tets, you can treat them as like degenerate hexes if you want to.
Yeah, that was the original plan, was to actually do that, and then we ran out of steam and money. So I don't think at the moment there is no, we are not doing that. So there was a plan to try to exploit that and see if we could get some performance out of it, but I don't think it's gonna happen anytime soon.
Well, so for reference, the NIC-RS codes I worked on back in grad school, we were all hex, right? So we could just ignore that issue.
Okay, thanks.